All right, let's get started. So welcome back. I hope everyone had a enjoyable and relaxing break. So we are towards the tail end of our course, and as I mentioned earlier last week, there isn't simply enough time to cover everything which I had originally planned for the third module. But that being said, we do have 3 more lectures after this, so we'll use all that time to at least cover intuitions of the concepts which I wanted you to learn in this third part of the course, and maybe we will spend a little bit of time going in depth into sort of one aspect of this module itself. But today we'll begin with this third part of the course. So far, the story has been that we picked the cyber-physical domain, we understood the domain, we motivated a very specific problem in that domain, and we used that as an excuse to learn about different principles of modeling, which is applicable to that domain, but it's broadly applicable to any sort of CPS problem, right? So we spent a great deal of time looking at physics-based models, and obviously the key takeaway was not that just those models are limited to systems which are similar to thermal systems like in buildings. They can be broadly applied. In fact, you have physics-based models for the electrophysiology of the heart as well, right? So if you have to draw an analogy. And there, the sort of the principle that we learned was the state space modeling, parameter estimation, and how do you set up that problem, how do you actually do the estimation, what's the underlying secret sauce. We then spent some time looking at a different problem space altogether, which was this problem of verifying safety and efficacy of medical devices, in particular implantable cardiac devices, which motivated us to go deep into model checking as the solid principle that we learned and took away from that. And then model checking itself had some forms of timed automata and linear temporal logic and HOOPAL that you played with and learned. So finally, in this last part of the course, my intention is to cover some basic concepts of data-driven modeling, which is complementary to both these previous efforts, right? So in the first part, you actually did data-driven modeling when you had the structure of the model and I gave you some data and you have to estimate the parameters of that model, right? So you already did some data-driven modeling in the first module. In formal methods, you can ask that, how do you estimate these timing parameters from real patient data, right? So that's a very valid question to ask. How do you figure out that these clocks that you have in your timed automata, what are these min weight and max weight times of those clocks? So how do you sort of figure or estimate those parameters, which has to do with real patient data as well, but we didn't go that route. So I wanted to motivate or show you a different CPS problem in automotive CPS. In particular, we will spend some time trying to see how self-driving cars work, and a lot of what makes them work depends on data-driven modeling, right? So it's a different flavor of generating some outputs from that inputs for the system, which is a very complex system, I might add. And so we will look at how it works, and then we will go maybe deep into a little bit of deep learning, which is really what my original intention was. This is not meant to be a replacement for a machine learning class, so don't think of it as a replacement for a machine learning class. We simply cannot cover all of machine learning. I would even say we simply cannot even cover all of self-driving vehicles. That itself can be a course on its own. In fact, I teach that course for undergrads here. It's a semester-long thing. But what we will cover is the data-driven aspects of self-driving cars. And then again, we'll pick a very targeted example of what we call end-to-end driving, which is generating control outcomes or outputs directly from pixel data or from images without having to engineer any features yourself. Right, so I really like this hypothesis, and I think we are operating increasingly under this hypothesis that when it comes to mobility, everything which is moving will eventually become autonomous, and then won't require or very minimal, it will require very minimal human input. And it's not just true for self-driving cars. We are talking about any form of mobility at every scale whatsoever. It's trucks and even last mile mobility in terms of delivery, in terms of aerial vehicles as well. So in my opinion, it's a really, really good time to be working in this area because there's so many problems, more problems than we have answers, which is always a good place to be when you are a researcher. And so we have tons of problems in this space related to safety and how do you ensure that you can even trust these systems? How do you look at sort of a combination of systems rather than a single system on its own? And so there's a lot to be done here, and it's a big domain, autonomous systems themselves. But we'll sort of focus on mostly self-driving cars or autonomous vehicles, right? And that itself is a really, really huge space. This is just to give you some context of what this modern transportation stack looks like. And so every logo you see here is some business, either it's a tier 1 automotive manufacturer or some startup or some company working at everything from sensors all the way to different layers at the infrastructure, looking at safety and security of self-driving cars as well, to services like Uber is a service in terms of ride share, and that could be completely autonomous as well. In fact, there's a very great likelihood that the next decade or somewhere in the next decade to 15 years, transportation will become very similar. Road transportation will become very similar to air travel today, right? So when you travel today, you don't necessarily care if you're traveling in a Boeing or an Airbus. You are loyal to mostly the services or the airline, if you will. And so that's sort of the model where we are headed, where it won't really matter if it's Waymo or Tesla or who's making the actual car. It will be the service layer or the application stack where we'll be mostly engaged in this kind of autonomy. So we are making progress towards that every day. This is such a big space that every day there's something new happening in self-driving cars, in automotive cyber-physical systems as they are. So if you don't already know, there's different levels of autonomy or a scale when it comes to talking about self-driving cars. I won't go into too much detail about what differences there are between one versus the other. But the scale is taking you from zero autonomy or completely like stick-shift manual vehicles where the human has to do everything related to perception, planning, and control, all the way to these pod-like future vehicles that we envision where there won't be even your steering wheel or a gas pedal inside it. Right? So very connected, fully autonomous vehicle that you just sit in and you are more productive with your time rather than waiting and getting stuck in traffic. There's obviously the biggest use case for them in terms of safety. Majority of accidents occur because of human error, more than 90% in fact. And so if we can reduce that number ideally down to zero, but that's very, very hard. But if we can significantly reduce that number compared to human errors, then that already is very, very beneficial in terms of its impact. And then there's marginal benefits as well in terms of sustainability, better traffic management, better use of infrastructure, so on and so forth. Right, so I don't want to convince you that self-driving cars solve a lot of problems, but we want to quickly jump into what makes them work, or what is the data-driven portion of why these cars work and how do they work. Again, just to give you some very recent view of the landscape of how the scale and both the pace at which things are progressing. This is a very recent snapshot of the permits which were obtained by manufacturers to drive and test their autonomous cars in California. And so you can see it's a long list and there's some key main players, but the important part is that everybody has some skin in the game and some agenda when it comes to this very, very promising technology. So as someone who's a researcher in cyber-physical systems, this has the potential to integrate and even expose many, many different problems. Right? So you don't need to be just someone who is interested in AI and machine learning to be able to work in this area. Even traditional sort of fields like real-time systems and embedded devices or formal methods, whatever the sort of stuff we spent on in the previous module, and first principle-based modeling as well, all of that is very, very relevant in this single domain. So very quickly, what's sort of the anatomy of a self-driving car? It has a bunch of different sensors. These aren't the only sensors, but you can imagine you have a car. It has LiDAR, which is just bouncing off these. Make sure it's visible. It's bouncing off these rays, and it has radar. So radar can be a much more long range, but it's much less resolution than a LiDAR. LiDAR is very, very high resolution. And of course, you have visual perception or cameras, which tell you about the traffic scene around you and where you are with respect to your surroundings as well. Right, so we have all these sensors on a car, and there are other sensors too, ultrasonic sensors, GPS, and even different forms of LiDARs, solid-state LiDARs versus mechanical spinning LiDARs, which gather information and data essentially about the surroundings of a vehicle, and we build on that data set to then make decisions about how a vehicle should drive, right? So that's sort of the self-driving car problem. How do you go from data to decisions? And so regardless of who builds that car, they all follow somewhat of a similar logic. All that logic is not necessarily safe right now, so that's the big question in this area. How do we ensure safety of self-driving cars? So this is still, in my opinion, a technology which is in its nascent stage. So it's undergoing some very accelerated testing, which is good for this industry, but there have been some very prominent failures where it resulted in the worst case possible outcome when it comes to why we need these cars in the first place, right? So there's a lot of political hype, there's a lot of regulatory issues with this. We want to sort of detach a little bit from that and just focus on the technology for the most part in this module, and talk about and understand what is this data-driven models, what are the family of data-driven models which are responsible for accomplishing this task of driving. Right? So driving is a pretty complicated task if you think about it. We do it without even thinking twice because we have gotten very good at it and we have years of practice. And in fact, the human brain is a pretty powerful machine, so we can multitask very, very easily without sort of burning ourselves very quickly, right? So over long distances, we do feel fatigue, even when we drive in the real world. So there are some aspects where computers are better than us. We can't fatigue them. But at the same time, there are aspects where we are much, much superior than sort of our silicon counterparts. So regardless of what self-driving car exists out there, every car has to solve these problems, right? So every car has to figure out, firstly, where is it? Where am I with respect to my surroundings? So that problem is one of localization. And so you sense all this data to figure out where you are. You also sense this data to understand the scene around you. So the scene understanding or scene parsing is, again, a very complicated task. So you need models to identify what your surroundings look like, what are the other vehicles in your surroundings, where's the stop sign, where's the traffic light, where are the lanes, where's the vegetation, where's the barriers. Then once you have a knowledge of what the scene looks like and where you are in that environment, you want to figure out where do you want to go next, right? So the driving is a task where you continuously have to figure out what you want to do in the short term and both in the long term. And so every car out there does this loop of sensing and planning and then action, right? So we've seen this as a hallmark of cyber-physical systems in general, where there's some closed loop. And so here, the closed loop is perception, planning, control, perception, planning, control. And also there's a need to study and reason about and improve the interaction of the vehicle with the passengers inside them, right? So at the end of the day, we are making these vehicles for humans, and so we shouldn't put the human out of the loop of this cyber-physical loop. So even understanding human emotion and how that pertains to driving behavior is a very, very interesting problem on its own. Right, so there are many ways to do localization and mapping, and once again, this is not a course that talks about each one of them in very detailed level, but I'll give you some examples. So visual odometry is one idea from robotics, where essentially they're trying to mimic how we localize ourselves. So when we walk, we identify features. So I know this is Thornton Hall, I know that is Link Lab. I have a map inside my brain because I've visited this place before. And so visually, I can look at these landmarks or features and sort of figure out where I am in the world. And so that's the high-level concept with visual odometry, only that it's not as easy as I describe it to be. So we have some very seminal algorithms called simultaneous localization and mapping, which try to mimic this behavior, right? So where you are in the world, you are looking at some features which are detectable in this environment, and based on how far they are and which cluster of features appear in what orientation, you can identify or infer what you call your pose in the environment or in the world around you, right? So this is just one example of how you localize and how do you build maps. This is done using just cameras, but as I said before, we have a variety of different sensors. So ideally, you would fuse data from all these sensors to do similar stuff. And it's fine to, if you don't know what SLAM is and how it works, this is just an example. So let's talk a little bit about scene understanding. Here, the problem is one of object detection, but it's much, much more complex. It's dynamical, it's not static, and we can't really have a predetermined list of all possible objects that you will see, right? So it's much harder than even traditional computer vision-based object detection. But so in the past, again, the way you would have solved this problem is you would have some template for what a car looks like, and you can scan an image for which part of the image best represents my known template. And if I find a good match, then I would say, here is where I have found a car in my image. And so you could build templates for stop signs, for traffic lights, for pedestrians and cyclists, and you would do that. So you have these classical approaches where you have these templates are sometimes called these cascaded classifiers, because you are running one after the other of the same image. And some recent advances have made this problem much more efficient and easier to solve. So this is sort of state of the art right now. We are given some video stream or given a scene where you have other dynamical instances of objects as well. It's a pretty complicated scene. There's traffic lights. This is like real world driving. And semantic segmentation is one idea where you are assigning a class label for every pixel in what you see, right? So you're seeing road networks or vegetation or a pole, and you have the list of classes on the right-hand side. And so we can train what we call neural networks to do semantic segmentation. And again, this is very useful. It's also useful in medical cyber-physical systems where, given an image, you want to detect some cell types or presence of tumors and things like that in a slide. Semantic segmentation has been proven to shown very effective for such problems of pattern recognition. So finally, you understand what the scene is, so you know what different objects looks like. You need some logic to combine all that information into some kind of plan, right? So at the very least, your plan is not to collide, right? So at least that's one objective, but there can be many objectives on top of that. Not only don't you want to collide, you want to have smooth transitions, or you want to make sure that there's no abrupt changes in steering or acceleration unless they are required and there's an imminent collision. So you have, and then again, you want to even predict, not just detect what is happening, you want to predict what other agents are going to do and take that into consideration when you plan. Much like how we do driving ourselves, we are very good at gauging the traffic situation in front of us and figuring out if it's safe to overtake right now, or what's the relative speed of something in my blind spot or something I see in my rear view mirror. So if a car has, in theory, a much better perception module, because a car can see in domains outside of just RGB spectrums like you and I do, it can see in a much wider field of view as well. So in theory, it should be able to plan better as well. But again, problems are not as simple as I make them sound. But at the very sort of canonical form, the problem is, where should I go and how much should I accelerate? And when I say accelerate, I also mean decelerate. So braking is taken into account. So this is actually a very interesting video. This is sort of a visualization of what the Tesla autopilot does today. It's not from Tesla. So this is some groups who have reverse engineered autopilot hardware to get us some sense of what that hardware is capable of doing. So the disclaimer is this is not what Tesla does, or that's not the claim, but it gives us some idea of how they are doing some kind of trajectory planning, right? So you see this big yellow band in the middle, and of course the car is also able to detect these traffic lights. It's just not being highlighted in this visualization, but these different color bounding boxes are some sense telling us the scene segmentation or scene understanding of this autonomous car using just camera, right? So these cars are known to have only cameras and not LiDARs. So it has different categories for motorbikes with the blue bounding box, for a pedestrian with yellow, and for a vehicle with red. There's this green patch, which is their inference of drivable surface at any given point. And of course, there's the lane markings which are detected as well. So this is much more chaotic because this is in the middle of a street. Here is some freeway traffic, much more structured and disciplined. So you can see that the car is detecting lanes. It's trying to maintain its lane. It's detected that there's a vehicle in front. How fast it is moving as well is part of this planning process. So it can get very complicated very, very easily. And this is on top of after you have done your localization, mapping, and scene understanding, right? So these looks like these purple markings are detecting the edge of the entire freeway itself, but the car even has knowledge of whether something is in your lane or not, right? So if you look at this tag over here, it detects this vehicle, how far it is, how fast it is moving. It assigns it an ID as well. So that's some temporal information. So every frame is not assigning new IDs. It's keeping track of, oh, this is the same vehicle I saw previously as well. And then it's giving you some context of whether the vehicle is in your lane or the left lane, and how far in the left lane, what is the velocity, things like that. Yeah.
How does it tell if it's the same vehicle or not?
Using neural networks as well. Okay. Right, and then finally, the key piece is also human interaction, more so for sort of a level 2 to level 4, level 5 autonomy, where the idea is that in the business as usual traffic conditions, you can rely on the car, but you have to be prepared at all times, or there has to be some graceful way of handing off control back when the car is not sure of what decision to take themselves. Right? So this is a very, very huge area. Again, you're barely touching the surface of this, but there's a lot of work on detecting gaze and driver attention and driver emotion. And how do you take all that context into account to design interfaces that allow for this graceful handoff as well. So this is a sort of a 30,000 feet view of this area of self-driving cars, and at the very least how every car works. But now we'll get into some specific use case of these self-driving cars. In particular, I want to touch upon this notion of end-to-end learning, which is what the emphasis of this module is going to be on. And so what we have observed in recent years is a lot of this perception planning control pipeline is getting offloaded to this deep neural networks, which I'm sure everybody has heard, even though you may not have understood or you may not be familiar with how they work. But I'm 100% sure everyone here has heard this term, deep neural network, which seems to be this magic oracle that you feed a problem and it will solve your problem. And in particular, perception has had the most heavy usage of these deep neural networks, but in some cases, even the planning part, even figuring out this trajectory, figuring out the steering and the control inputs to accelerate your car are now getting generated by some of these networks, right? So they're not yet readily deployed, but that is where there have been some recent developments in this domain. And so, since a lot of these networks rely on data from the real world, at the end of the day, it boils down to this very simple premise that machine learning is largely about situations that you have seen before. In fact, this is not entirely true. The true statement is supervised machine learning is entirely about training data you've seen before. So it is a problem, and how do you understand all these scene parsings and localization and planning and do this in a manner which is safe enough and reliable enough? Because just like the medical CPS domain, I would even say automotive CPS is a life critical and safety critical use case, right? So it's one thing to use a deep network to sort of detect cats and videos, and occasionally, if you have a 94% accurate network, 5% of the time you'll misclassify something as being a cat when it is not, but then nobody dies because of that, right? So, or maybe, if it's a car detecting a cat, then the cat could possibly die. But that's even that level of accuracy is not good enough for driving, right? So would you sit in a car if you know there's a 5 in 10 chance or 5 in 100 chance of running over someone, right? So you would never sit in that car. So it's a very hard problem. And just to motivate that, I don't know if we have audio. Let me see.
A new video is exposing a potentially fatal flaw in Tesla's autopilot feature.
I was on my way to work today. I drive up and down 101. I decided to test the subsection of the road where that autopilot accident happened. So I took a quick video, or I tried to actually, of that section of the road where 101 splits off into 85 on the left. And the results are kind of freaky. So it's not great because I low-key freaked out, but the car definitely sort of starts swerving left without giving me any warnings right into that divider.
You can actually see the steering wheel turning left while the blue autopilot light is on. The driver in the video says he got scared and took the car out of autopilot as it was headed toward the divider. An engineering professor told our San Francisco station that the camera attached to the Tesla was having trouble seeing the lanes because they aren't marked clearly. This video comes after a crash last week in the same location. You heard the YouTuber make mention of it. Tesla confirmed the car was on.
Okay, so first of all, I have nothing against any particular company, right? So don't take this as my personal agenda, but this is just to show that these are real problems. And the reason I'll show some of these examples is something that my research group works on, so it's easier for me to even talk about this. But here's some examples, right? So how do you classify this if you are a self-driving car? You have a image of a cyclist, which is just a sticker behind another moving vehicle. So it's not that even you can detect that this thing is not a pedestrian because it's not moving, because you will detect the cyclist moving at the same speed as the car. So if your local planner takes all of these variables, just like we saw Tesla detects all these different variables into account, then you would act differently as if there are cyclists on the road, whereas the matter of fact is that there are no cyclists on the road, right? So how do you detect, or what do you do in this situation where you have many cars? Do you detect this as one car or multiple cars or cars in the z-axis? Does that even make sense for some autonomous car to even detect and infer? And how do you then react accordingly? This is my personal favorite. So in Japan, there's this ramen noodle place whose logo looks like a do not enter sign. So how do you distinguish this from a do not enter sign, right? So,
Yeah, I just think this brings up an interesting point. Like, these are accidental adversarial examples, right? But, I mean, are people planning for people to generate, like if they have their own car, they can just purposely generate perfectly adversarial examples, right?
Yeah, so adversarial machine learning is very, very active in this domain as well, yeah. There have been instances where you can put some stickers on a stop sign that would still read a stop sign for a human, but a car would consider it as some bizarre traffic signal or even speed up in some cases. Right, so this is real. You can see this prototype Honda vehicle, it detects do not enter, whereas there's no do not enter sign, it's just a restaurant advertisement, right? So here's another example. The car thinks there's a bus next to that, but it's actually parked in a garage. And so the circles on the laundry machines look like tires, so you can't really blame the neural network. But the point is, these are real problems, and they lead us to this big question of how do you ensure that these vehicles can drive safely when they encounter these cases in the real world. Right, so it's a very, very hard problem, and by no means is it solved. So it's a very active area of research as well, but this is just to motivate you in terms of why are we looking at these problems, and in particular, why do we care so much about how to learn how these deep neural networks work. So coming to the actual focus of this last few lectures, we will look at how deep learning, in particular deep convolutional neural networks, and if it's jargon to you right now, at least by the end of 3 lectures, you will know what they are and how they work. And so the goal is to look at how these convolutional neural networks can help us drive, right? So given some complicated scene, in some, some kind of an arbitrary environment, arbitrary lighting conditions, there's even reflections of the camera itself on the windscreen and things like that. Can you at least predict how to steer and accelerate in this situation while, let's say, being in your own lane? Right, so this is an example of sort of what we will learn or understand how this works. That given some scene, can we design a model? So the course is about building useful models. So can we design a model that can predict how to steer as the road curves, or how to even speed up as the road curves, and how to react to other vehicles in my field of view as well. Right? So at the end of the day, all of what I described, the perception, the semantic segmentation, the planning, and all these neural networks, they're nothing but different kinds of models. In particular, they are purely data-driven models, and we'll see what sort of advantage do they offer over traditional way of building the same components. So a lot of what we will look at is motivated by this. Now it's a little bit dated work. At the time, it was very, very recent. This was a paper in 2015, 2016 by some folks from NVIDIA, which introduced this notion of end-to-end learning. And the idea being that end-to-end means that you look at image and you directly obtain some kind of control action from what you look at, right? So there's no intermediate human-generated factors or some kind of a physics-based model or some kind of a timed automata. None of that. We look at an image and can we generate control actions. Why do we think it's possible? It's possible because that's how we drive. Right? So we look at an image and we automatically generate steering and acceleration values. So can we design a model that given the input, which is an image, the output has these controlled actions? Right, so this model is nothing but a deep convolution neural network. In this paper, we have come a long way from what is described here, but we'll use this as sort of the baseline benchmark to talk about some of these ideas. Right, so we are learning or tuning this deep network, and we'll understand what is it that this network does. In the full module, I would have gone very, very deep into deep learning, like I said, to really understand all these ideas, but at least this week, I want to first just give you intuitions of how these things work, because if your intuition is right, then the mathematics will follow, right? And that has been our trend with the other modules too. We try to build intuition for why something makes sense, and then we apply it and use it for a problem. Okay. By the way, we can also do this on some of the vehicles that we have in our lab, if this video works. Which it does not. Okay, I'm sorry, this video is acting up, but I'll show you this next time. But in our lab, we have the ability to drive end-to-end on a 110 scale platform. So just like that Tesla was driving, you can very easily replicate that using similar architectures that are described here. I don't know why this is not working. Okay, at least this works. So this is sort of the equivalent of that same concept, where in this case the network is only predicting steering and not acceleration, but in principle there's nothing stopping you to predict multivariate outputs as well. So the blue steering wheel is the prediction and the green is the ground truth, and just based on this driving data for a few laps, the network has figured out or learned in some sense how should I steer in order to avoid crashing into this barrier. So here's the basic idea, which is the following, that you get some annotated data. So this data is sensor data, which is primarily camera, so front-facing camera, or you can have multiple front-facing camera with slightly different orientations and tilts. And each of this image of the camera is tagged or annotated with actuator data. So actuator in this case is the steering angle and the brake pedal and the gas pedal position. So you gather all this data, and then you build this magic box or a convolution neural network. And this network is essentially learned how to predict the actuation given a new sensor data. So given an image, can I predict steering and gas and brake positions? And this is not something which is very, very recent. This has been well known and well documented for more than 2 or 3 decades ago. In fact, in the very, very early days of neural networks and AI, this problem was one of classification. So a classification problem is one where you are just predicting some label out of, say, k categories, or only k finite possible values. So in this case, you only have 3 things that you can do. You can go straight, you can turn left, or you can turn right. And so you have reduced the driving or the steering angle prediction problem into a classification problem that, given an image, tell me what to do. Go straight, go right, go left. Obviously, this is very limited because the very natural question to ask is, well, how right, or how much left, or how much straight, or things like that, right? So the true problem is not classification, it's regression. So whenever you predict something continuous, that's a regression problem. If you're predicting categories, it's a classification problem. So in the very early days, autonomous driving looked like classification. Now we can do regression and multivariate regression very, very easily. And all of this is obviously based on machine learning. Like I said, this is not a course on machine learning, but I will introduce some key terminology that we will then use later when we talk about these neural networks. So essentially what machine learning is this notion that you don't have to program for every possible situation, or you don't have to program even the behavior of this input-output matching. If you give enough examples to this system of good behaviors or whatever behaviors between inputs and outputs, then the system can learn itself. So it can, if you think about it, it can actually program itself. And by program, we only mean figuring out the logic or the functional mapping between the inputs and the inputs, but otherwise a human would have to specify, right? That if you see a tree in this part of the image, go left, go right, that's human programming. In machine learning, you give it examples of how to drive, and the system will learn how to drive itself. Neural networks itself, they became very popular because United States Postal Service, they wanted to figure out where the address, what the address on the envelopes are, because people write in very different handwritings, so they wanted to create this computer vision system that can look at that can scan basically an envelope and tell you what address to send it to. So because of the amount of volume that they were getting, and now they face the inverse problem where nobody wants any letters, right? So again, some more terminology. I said this earlier without explaining. Supervised learning is nothing but learning from these labeled images or labeled examples. So you show me an instance of correct behavior, or you show me an instance of my end goal, and given enough instances, I can choose some model. They don't have to be always neural networks, of course. I hope that's obvious. I can create a model that can produce labels given new data that I've never seen before. Right, so that's the whole area of supervised learning. Majority of research is done in supervised learning. Majority of self-driving research is also mostly in supervised learning. Reinforcement learning is the idea that, well, one limitation of supervised learning is that getting this training data is very, very hard. Right? It's not cheap to get labeled data. Even if you were detecting, say, water bottles in images, you would need several thousand images of different kinds of water bottles, different colors of water bottles made out of different materials with different reflectivity, different poses, some partially occluded behind some object. So you need a very wide variety of labeled data, and so getting that data is actually pretty expensive, more expensive than training the network to detect the water bottles in the first place. So reinforcement learning is the idea that we may not need fully labeled images, but if we can tell our network that if you take some action, whether that action is a good action or a bad action, or to what extent is that action good or bad, this is a feedback to the learning process in terms of what is called a reward, then this machine learning algorithm can self-learn over a long period of time by doing enough exploration and exploitation of different possible actions and observing different rewards to figure out really good policies of how to behave in a different environment. And again, this is very high level because we'll mostly be talking about supervised learning. And the holy grail of machine learning is really unsupervised. How can we infer new things about the environment, or how to act in an environment when we are given no labeled instances of how to act or how to behave, right? So this is a very hard problem in general. This is really where some of the biggest challenges in this very, very broad field of machine learning lie on making progress in unsupervised learning. So one example of unsupervised learning, which is somewhat within our grasp or realm, is given some data, can you automatically figure out how many different types of categories exist in that data, right? So how is that useful? So instead of me giving you those 15 labels of semantic segmentation that I just showed you, can I just show you videos, and can you figure yourself what are the different type of objects which exist in the real world? So can you come up with the correct number of categories yourself without me having to tell you or give you labeled instances that this is the class of every pixel in this training example. Okay, so let me speed up a little bit because I want to get to the most important part quite sooner. Just a little bit of background. I want to make sure everybody, at least when you finish this course, you are very clear in how these three terms, which are very, very buzzwordy and very, very oftenly misused, relate to each other. So AI is a very broad field, in fact, the oldest field is AI with this notion. So ever since we had computers, we had this vision that computers would do everything that humans can do. And so that is the big, big goal in artificial intelligence. We don't even know fully what intelligence means. So creating artificial intelligence is still very, very tough. In fact, the whole reason why sort of AI existed was to break down these tasks. So if you look at a human, what sets us apart from, say, other species is firstly, we are very social compared to everybody else, but our visual cortex is very developed. So computer vision became a very, very relevant problem. So if you could replicate the same capability as humans in vision, that was one big goal of AI. Speech was the obvious one as well. So you have seen many, many advances where now you can barely distinguish whether AI is calling you or a real human is calling you. There were some demos by Google earlier this year. And then language is another one, right? So natural language processing has had many, many advances. But those aren't the only things which govern intelligent behavior. So defining what constitutes as intelligent behavior itself is a problem, but I think everybody here agrees that driving is a pretty remarkable intelligent behavior. We don't see any species driving any kind of vehicle. So it definitely has a very higher bar in terms of this goal of AI. And so a subset of AI, so even neuroscience is another part of AI, but from the computing side of thing, the subset of AI is the field of machine learning because it accomplishes most of these very hard tasks of vision and text and speech and inferring data in general. Makes it much easier. And so machine learning, again, very, very old field as well. And then a very, very small subset of all of machine learning is what deep learning is, right? So it's a very special case of this general ability to learn from examples or even reinforcement and unsupervised machine learning. Okay, so this is more semantics, not too related to what we want to really look at, but I'll introduce it. So since I said that very early forms of driving were classification, there are some metrics which are used to figure out whether your model is producing some good classification results, right? So let's look at the problem of detecting cats in videos. If I've seen many, many labels or instances of cats in videos, I've built some model. How do I figure out that model is any good? Here's one way to look at this. Anyone knows what this is called? There's a special name for
Confusion matrix.
Yes, right. So it's called a confusion matrix. And the idea very quickly is that if I knew this was a cat and I predict that this was a cat, then this is a true positive. Positive just means that you are predicting the same class as the ground truth itself. So this is a true positive means that it was a cat and I got it right. A true negative means it was not a cat and I got that right too. I predicted that it is not a cat. That's why it's true, and negative just means it's not a cat. A false negative is when I predicted incorrectly where it was a cat. And a false positive is I predicted something positive, which is why it's false, when it was not a cat. Sorry, yes. A false negative is when you predict something incorrectly when it is a cat, and a false positive is the inverse of that. So given these definitions of all of these, the point really is, without going into too much detail, that you can define some metrics called recall and precision and most importantly accuracy, which simply looks at the proportion of things you are predicting in terms of true positives and true negatives and false positives as well. And that gives you an indication of how good your prediction is. Right? So this is just to tell you what this means, not necessarily where it is coming from. It's coming from statistics, but we won't go into that. So let me skip actually a few slides and get to this part. So the idea in supervised learning is that you are given some data X, let's say you're given n samples, and each of the samples has some label, right? So we are still in the realm of, say, classification, but it also applies to regression. So this X could be an image, and that's data, and Y could be the staging angle for that image, which was obtained when you were driving in the real world. And so given this pair of sample and label, I have a function that I want to learn which will predict the label for each sample, and I will compare my prediction with the ground truth and compute something called a loss. And the goal of my parameter sort of adjustment is to figure out the values of the parameters of my model, which are denoted by theta, such that this loss is minimized. Right? So you've already done this. You've done this when we had the state space model, which had parameters, the resistances and the capacitances. The loss was least square, and we spent weeks and weeks looking at how do you solve this. So what's the class of algorithms used to solve this problem? Gradient descent, right? So we use gradient descent to solve these very, very nonlinear problems, and the same thing applies here. And so what I will describe next is what shape and form does this take place in the context of a neural network. Okay, I'm going to again skip over some more examples I had. Okay, so let's talk a little bit first about why do we want neural networks in the first place. So like I said, traditionally, let's say if we had to detect whether there's a car in an image, you would have something which was feature engineered by a domain expert. So if you were someone who was doing computer vision in the late 90s and the early 2000s, you would design a template which I described of what a generic shape of a car looks like, or you can have multiple templates of what the body of the car looks like, what the windshield looks like, what the bonnet tube looks like, what the wheels look like. But these were sort of human derived, right? So we needed some domain expert to come and define these templates for us. And then you would run your templates on your image, find areas which have the best correlation with different scales and rotation of the templates. In fact, this is very effective, but it has a lot of manual labor involved, right? So the traditional model was that you had these engineered features, which was a main bottleneck, right? So this is why the vision problem and the audio speech problem and the natural language problems were very, very hard, because people had to look at dictionaries for language and define grammar rules, syntax possibles. Vision is very hard. It depends upon the classification of what type of objects you want to see. Speech was very hard. You wanted to look at pitch and frequency and this other feature and the peak and amplitude of your speech and some basic tonal properties. So these are all engineered features, and once you had these features, you would build a model for given these features and given this label, can my model predict the correct label from these features? What deep learning or end-to-end learning has really changed is the fact that you don't need to engineer these features yourself. So you just can go from raw data of any form. The only property that you really care, and you will see this on Thursday, is that the data should have this property that things which are close together in some sense, where close is a loosely defined word, are related to each other, right? So in a car, the pixel, which is the door of the car, is very, very highly related to pixels in the vicinity of that very pixel itself. Right, so there's any pattern whatsoever is a pattern because there's a relationship, spatial relationships between adjacent pixels. In audio, what I say now is very closely related to how I started raising my voice and how I emphasize certain words or take pauses. So they are temporally related, right? So that's the key property which allows us to really use some of these very nice ideas that the features themselves are not engineered anymore. You can learn them, or they are part of the modeling process themselves. So it reduces this burden of generating features, which is very, very limited by our domain knowledge and is not guaranteed to scale properly or work in data sets which are slightly different from what we designed the features for. So instead, we want to go to a paradigm where feature learning is part of the entire process of learning itself and not necessarily something which is hand-generated, right? So this is a better way to explain that same idea. So traditionally, you would have, say, camera, and you had hand-designed features. So where the lanes are, you can have an edge transform for detecting lanes. You can detect trees by using template matching and other cars as well. Then you build some machine learning model And the input to the model was not the image itself, but the features that you extracted from that image. And based on that features, the model produces some kind of a scene understanding, which is then sent into some other domain-specific path planner. So a path planner may have the actual dynamical model of the car. It could be a state space model, and then you would have even like a advanced controller to figure out how to drive. So everything which is in blue in this pipeline was domain knowledge, right? So human had to physically and manually specify the properties of each of these blue blocks, and the learning was just one sort of a part of this entire pipeline that took you from perception to control. And what end-to-end learning has done, and deep learning in particular, so deep learning firstly has combined or solved this problem that in order to learn something useful from data, you don't need human engineered features. You can learn both the classifier and the feature together. And then finally, we have end-to-end learning where the idea is that there is no human input needed to go from raw data directly to your control. So everything, including the path planning and the control, is learned in one shot. End-to-end describes really going from this end to that end in a single shot. All it really needs is a lot of training data. So nothing is hand-designed in this pipeline, but that's not entirely true. So the human input is no longer needed to do feature engineering or path planning or control. What it is needed for is figuring out where this data comes from. So humans have to provide examples or label data from the real world. Humans have to use still domain knowledge to label the data correctly, and you will see examples of that. And finally, there is some art to setting up this pipeline, right? So there is that hyperparameter tuning, which is still semi-human driven and semi-autonomous today. Right? So although the learning itself has become end-to-end, there is still involvement of how to improve this learning pipeline, both from the data side and the actual implementation. But still, this is much different and useful in some sense than doing this traditional feature engineering approach. And it comes with its own pros and cons, and that's a topic for a later lecture. Okay, so finally, the task that we will look at is the following, that we will be given some images, and each image will have a wheel angle value or a steering angle value, right? So in fact, we'll be only looking at mostly center camera images and ignore left and right cameras. So for every image, we'll be given a steering angle, which was the angle that we logged when the human was driving. And we'll build a neural network end-to-end such that given a new image, we can directly predict what should be the steering angle for that image, right? So we are not doing any lane detection or semantic segmentation or path planning or PID control. None of that human engineered feature engineering has to be done. We will design a machine learning algorithm that will look at the pixels of any image and predict the steering outcome directly. So it's doing end-to-end learning, which is what the emphasis of this module is. Okay, so that's what we are going to do, driving with a single front-facing camera. And time permitting, we may visit this notion of the reason why we want to do feature engineering or why people did feature engineering was that they could reason and understand why some action was being taken, right? So they could explain the actions of their entire pipeline. When you train end-to-end, you lose that aspect very, very heavily, right? So the network may be able to generate correct steering predictions, but when it mispredicts a steering, when it crashes you into the wall, it's very hard to explain why that happened, right? We saw examples of, it's very hard to explain why the washing machine was getting detected as a bus parked next to you. So that's a sister domain of explainable AI, in particular explainable deep neural networks. So at some level, the intuition is that you will learn that something called the receptive field of a network, where we can visualize what the neural network is paying attention to when it is making some decision. Right, so let me see how much time we have. Okay, so with that, let me get the problem warmed up, and we may not have enough time to go into all the details today, but I still want to introduce this. And so we will begin with a very intuitive understanding of how neural networks work, right? So this is not a rigorous mathematical introduction. If I was teaching a machine learning course, this would not be how I start. And certainly I would never start from the biology of a neuron and how that motivated a network. We'll get to all that stuff later. Today, I just want to give you an intuition of what is a neural network and why does it work? How is it able to do classification, right? So that's our goal today. And so to do that, let me begin with an example. So let's say we have an image. Our image is just a 4-pixel image, right? So not 4 megapixels, it's just 4 pixels, so 2 by 2. And our task is to build a model that can look at this image and tell me whether this image is a solid, which means all the pixels are the same color. Is there a vertical line in that image? Is there a diagonal in this image, or is there a horizontal line in this image, right? So those are the 4 classes that I want to predict given this 2 by 2 image. And I say that maybe for this simple example, doesn't apply, but in general, simple rules or simple programs will very soon hit a ceiling that they can't just come up with a set of rules. So give you an idea, you may write a rule that if the top 2 pixels are white, then it's a horizontal, right? So, but what about this case, right? The top 2 pixels can be black and it could still be horizontal. So you need another rule for this. But now you have set a rule about the properties of these pixels. What about different diagonals, right? Where this rule gets violated. So writing rules or programming from feature engineering or classical vision techniques will hit a ceiling very, very soon, even for the simple toy problem. And so we take it for granted that when the size of this image is very, very large and our labels of interest are not these simple shapes, it becomes even harder to specify these rules. Right, so what we will do is we will learn how a neural network solves this problem. So let's first just keep on going with this example and see where it takes us in terms of what a neural network does. So there's something called an input neuron, and don't worry about why it's called a neuron, just try to understand the functionality. So in this case, we have 4 input neurons, and simply put, each input neuron is just mapped to 1 pixel of my input image, right? So every pixel is just telling me the value of the color of the grayscale image for my image itself. So I have some kind of a spectrum where if the pixel is fully white, it has a value of +1. If it is fully black, it has a -1, and gray is like 0, right? So somewhere in the middle is gray. And so my input neurons have the property that they just are simply reading off the value of every pixel in my input image, right? So that's just an example to be shown here. So this is almost like an input vector. So my input image is 2D, but my neurons are a single vector where every element is 1 pixel. And so then it's very intuitive or very useful, rather, to think of a receptive field of a neuron. So a receptive field is just the input image that leads to the highest possible value of my neuron, right? So in this case, if this neuron is meant to just read the top left pixel, if my input image contained a top left white pixel, this neuron will have a value of 1, which is the highest that it can obtain, right? So that's why a receptive field for every neuron is which input image leads to the highest value of the neuron itself. That's what is called a receptive field of a neuron. The black and white check mark just indicate that this neuron doesn't care about those parts of the images. And that's simply by design, how we have mapped our 2D image into this input vector. Right, good so far? So let's keep going. What we do next is very interesting. So we look at the values of these input neurons and we add another neuron with the property that I will sum all the values of the input neuron and provide it to my other neuron. Right, so we are building, so these, remember, are called inputs neurons, and now I'm building a new neuron. And to build that, the first thing I do is I sum all the inputs. So the example of that sum is just shown here, it's 0.5. But to make things more complicated, and you'll know the reason for that probably in the next lecture, I add weights to each of these input channels, right? So the sum is not a pure sum, it's a weighted sum, simply put. Right? So when all the weights are 1, the sum remains the same. When the weights are something else, you get a different sum, very, very obvious. Right? So that's the first thing I do when I build a new neuron. In fact, to simplify the picture a little bit, what I'll do is, if my sum is positive, I'll keep the edge white. If it's negative, I'll keep it black. And the value of the sum itself denotes the thickness of the edge itself, right? So when the sum is 0, there is no edge. So I simply won't draw that edge, just to keep the slide clean, okay? But nothing has changed semantically. So what you notice though is that due to these weights, the sum is very different from just simply adding the input numbers themselves, which was 0.5. Right, so what do we do next is, we are still designing our single neuron. So we just summed up all the input values with a weighted sum. We had an output, and what we do next is we take that output and we pass it to a nonlinear function. And that nonlinear function is very often the sigmoid function, which has this inverse, S-shaped function, right? So just to recall, this is what a sigmoid function is. So the input to this sigmoid function is the weighted sum, and I simply read off the value of the output, and that's the output of the sigmoid function, right? So, yeah.
Why is it a nonlinear function?
Well, it's mapping.
I mean, why does it have to be a nonlinear function?
So again, you will get the answer next week, but it's because, let me give you a precursor. It's nonlinear because the problem that you have of classification is not a linearly separable problem. So I don't want to confuse you unnecessarily what is linearly separable and what is not. But simply put, the advantage of adding neurons is to make the model capture nonlinear patterns in your data, right? That's the intuitive example. So mathematically, it's very obvious why this sigmoid will work well, but right now let's just first understand the machinery, and then we will, once we go into the mathematics, it will become very apparent why this is the case. Another reason why we would want something like a sigmoid is that the weighted sum could be any number between negative infinity and infinity. So we want to make sure that the output of the sigmoid is always capped between 1 and negative 1, right? So no matter where you are on the x-axis, the output is always less than 1 and between -1 and 1. So you have this sort of a squashing effect, which is what sometimes sigmoid is also called, right? So far we have a weighted network. Remember, the edges denote both the sign and the magnitude of the weights. We sum them up, we pass it through a sigmoid, and then we get a number between -1 and 1. Yeah?
Why were some of the weights negative?
I haven't explained, so yeah. So I haven't explained, and I will not yet, but you'll get to know it, yeah.
How is that different from a rectifier?
How is that?
Different from a rectifier?
So let me explain to others what a rectifier is, right? So I know it's good that you have all these questions, but let me go a little bit. No questions for 5 minutes, and then you will be in much better position, right? So the point I want to make is, we did this. Our original image had pixels between -1 and 1, right? That was the scale of the brightness of the pixel, or say the color of the pixel. And after we did this weighted sum and sigmoid squashing, this number is always going to be between -1 and 1 itself, right? Because that's by construction. So actually, this can be thought of as another input, because it's always between -1 and 1. Even though it doesn't make sense to what this neuron is doing right now, numerically, its value is no different from the values of our image. They may represent something else, but numerically they are indistinguishable from my image data, because the value of this neuron will always be between -1 and 1, just like my original image. So what I can do, in fact, is I can keep on building neuron after neuron. So passing this into another neuron and another neuron, and I'll explain why, because I see some blank faces. But before that, we have this weighted sum and squash neuron. We can create multiple such neurons, each one of them connected to each of the inputs. And once again, just to simplify, I am going to assume that our weights are either 1, -1, or 0. In reality, they could be any real number. But in this image, black is -1, white is +1, right? So that's sort of our weights. And so we can build 4 neurons in the next layer, if you will, or 400 or 4 million, and Later, I will also comment on some kind of a rule of thumb to gauge how do you do that. But let's keep going in our example to see what these neurons are doing. And like I said earlier, a good way to understand what these neurons are doing is to look at their receptive field, right? So earlier we had a receptive field which was just the input. Now we have slightly more complex receptive fields, right? So once again, a receptive field is the image that will trigger my neuron to take the maximum possible value. So look at this neuron, which is the first one in the second layer. I have a positive +1 from this image and a positive +1 from this image. So that means that this input image will lead to a +1 value over here, weighted sum and squash. Likewise, let's look at another one. So let's look at this one. This is a combination of this receptive field with a positive edge and this receptive field with a negative edge. So this neuron will reach its highest value when this is the input image. Why is that the case? Because when this is the input image, this neuron will be white, so +1. This neuron will be black, so -1. And -1 multiplied by a -1 edge would be something positive, so it would still lead to a positive value of my neuron. So this is the receptive field for this neuron. And the point is, which is another way to think about nonlinearity, that subsequent layers are capturing some complex patterns in my original image in terms of their receptive fields by doing this sum and squashing. That's the intuition. We haven't looked at the mathematics completely yet. So I can keep going, like I said, because each of these looks like an input image itself, because it has a value between -1 and 1, same as the input neuron. So I can add another layer with more edges, and I haven't defined how these weights are getting allocated yet, but let's say we have this image where the receptive field becomes even more complex. Right, so now you have, from a pattern of 1 pixel, this is already a pattern of 4 pixels, these receptive fields. So I can keep on going. It's up to me as a design choice, as a modeling choice, how I want to structure this. Then there's another type of neuron which is very widely used because it has some nice mathematical properties, and that is called a rectified linear unit. So a rectified linear unit is just another function, very simple function. If the input is negative, I set it to 0. If the input is positive, I let it be. That's the property of a ReLU, or a rectified linear unit. So I can add, and I know your number one question is why, or how do you decide which layer comes first? Hold on to your horses, I will answer that. But right now, let's just look at the repercussions of this, right? So we had a very complex receptive field. If we add a ReLU, we have even more patterns that we can now capture, right? So this neuron has a receptive field of all white, with the positive edge that remains intact, with the negative edge, it flips to all black. And basically you are getting different variations of your inputs after you do this ReLU operation. So we have this, and then just like we had an input neuron field, we wanted to classify into 4 different categories, so we'll have our output neurons as well. And simply put, if the receptive field of these neurons indicates the class to which my input image belongs, right? So this is an anatomy of a neural network, and let me give you an example to understand this better. So let's say my input image is the following, and for reference, I have shown the receptive field of every neuron in my network. The output layer doesn't have any receptive field because they are the labels themselves that we are interested in predicting. So this is my input image. So if I pass this image to my input layer, this neuron will take a value -1 because it's mapping to this one. This will take a value of -1. These two will be +1 and +1. So I indicate that with 2 black and 2 white neurons. It also makes sense intuitively. This neuron's receptive field was the top left pixel being white. And because the top left pixel is black, it has taken the lowest possible value of -1. Right? This is why you want to look at receptive fields. But let's see how this information propagates. So I have -1, -1, +1, +1. The white edges are +1 and the black edges are -1. So I can then propagate this information into my next layer. And what will happen is, let's look at this one. This has a -1 multiplied by a +1 edge, so the answer is -1, plus a +1 multiplied by a white edge, so the answer is +1. So the sum itself is 0. And therefore it is gray. Remember, gray was 0. Right? So same way you can determine that this will be also 0. And here you would have a -1 and a -1 itself. And without looking at the edges, just look at the receptive fields of this. Right? So this receptive field is the inverse of my image. Just look at the left 2 pixels. Right? This receptive field is the inverse of the pattern in my image. Therefore, indeed, its value should be flipped. It should be -1. And the same holds true for this one. But if you figure out the negative and the black and the white edges, you will also reach the same values. So we can keep going, right? Now we have populated the values of these neurons. Let's continue to the next layer. And again, without going through all the example cases, simply look at the receptive field in this case. This was the receptive field of this neuron, and this image is literally the inverse of our input image, therefore the value is -1. And all the others are 0, saying that it's very unlikely that these receptive fields are getting triggered. And then finally we have our ReLU layer, where because all of these are zeros, it doesn't matter what the weights are, 0 multiplied by anything, and a weighted sum is always 0. So the only thing that will survive is this bottom left or bottom right neuron, which tells us that our image is horizontal. So this is just an exercise to explain the machinery of what a neural network does. What we haven't told you is how do you adjust the weights of this neural network, or how did it figure out which edges to form and how to generate these receptive fields? Yeah.
So both the ReLU and the sigmoid, do they both have the point 0, 0?
You both have what?
Do they both go through the origin?
Say that again.
Do they both go through the origin?
Yes.
Yes.
Yes, both go through the origin. So questions on just the machinery, on why this network with these edges and weighted sum and squash function or sigmoid function and ReLU works for this image. And you can play with the diagonal image and have a field day, but I'm telling you this neural network will always classify any 4x4, 2x2 pattern. Okay, so the obvious question is how did this happen? So let me use the last 2 minutes to motivate that. And the idea is very similar to what you've already done. So here's we are leveraging some things that we already know, right? So fundamentally what we are doing is, the question really is that how did you come up with those weights, right? So why does your neural network look like this is the question. And the answer is that for any image, I have the ground truth. The ground truth is that this image is horizontal. So all the labels for these 3 classes are 0, and the only positive label is for the correct class. So I would have a training data for hundreds of such images. And for each image, let's say my network, instead of producing perfect prediction, produces some random garbage output. So it produces some score at the last layer. What I can do is, since I know the ground truth, I can calculate least square error, or at least the error, simply the magnitude of the error between the ground truth and the score. So this is equivalent to my loss function, and all I have to really do is very similar to parameter estimation that you did earlier, where given a loss function, how should you tune the parameters to minimize the error? But what are the parameters in this case? The weights of the edges. So given the number of neurons in every structure is a design choice, and you assume that all edges are connected to begin with and they all have random values, for subsequent images I calculate the error and I propagate it back using nothing but gradient descent to tune the values of each of the weights of the parameter. Now you can have millions of parameters, unlike your RC model with only a dozen parameters. So this gradient descent problem is very, very hard to solve numerically, which means that if I have some loss here, I can perturb a weight to see how my loss changes, and then I know I have to change that weight in a particular direction. But to do so for a million weights in a million dimensional space is very, very hard. So there's a very clever way to do that, which uses some very basic, simple properties of calculus, and that way is called backpropagation. So on Thursday, we will look at backpropagation, and then we will study a different class of neural networks called convolution neural networks, which are the basis for all of these problems of autonomous vehicles. So both of these lectures are mostly going to be intuitive flavored, so similar to these picture ideas rather than detailed in-depth mathematical analysis like we have been doing in the previous modules. But the week after, we will spend some time understanding at a much level of greater detail why this network works the way it does. So I'll see you on Thursday.